Okay. So the concept, because we kind of finished up last time talking about this, is if you have a situation, if you have some ring community identity set, and you've got some multiplicative set S, and you've got some little ideal here I, and their overlap is nothing, right? So it's got an empty intersection. You can expand I to an ideal P that is maximal with respect to missing S, right? Notice this is not the complement of S, it's just the biggest ideal or a biggest ideal that contains I and misses S. And this means that if you have any ideal that strictly contains P, but bigger than that, you automatically overlap with S. Any such P is a prime ideal. Here is a corollary that we got. Take any multiplicative close set that doesn't contain zero. Right? It's just let I be the zero ID. Since this doesn't contain zero, there will be no overlap. Great. So now you can grow I to an ideal that is maximal with respect to missing its multiplicative set, and that will be prime. If the set, if you further specialize and say the set is just the element one, which is multiplicative close set, then it will grow to an ideal that is maximal with respect to not containing one, which will be a truly maximal. So here is a nice characterization of saturated multiplicative closed sets. This is rather famous result. Let S and R be multiplicative closed set. And with and I want to make sure that zero is not in this particular set. The following are equivalent. Number one, S is multiplicatively closed and saturated. So it's multiplicatively closed and contains all its divisors from the ring. Two, SC is a U of prime. This is a very groovy theorem, because what it says is any saturated multiplicatively closed set is a union of prime numbers. For example, look at this. This is the powers of prime 2, including the zero power. Right? Notice, this is a multiplicatively closed set, because when you multiply 2 powers of 2, you get another power of 2, plus or minus, right? And it's saturated, because anything that divides the power of 2 can only be another power of 2 by unique factorization of the integer. Everybody agree with that? This is a complement of prime ideals. Anybody know what it is? That is correct. Well, actually, let me be more specific. Right. Complement this alpha. Right, or that's the most efficient way to write it. Or Pn is okay, this is a wonderful theorem because basically it characterizes all multiplicatively closed sets that are saturated in terms of being a complement of a bunch of ideals. Let's see how this works. let's do 2 implies 1.
For number one,
Uh-huh.
isn't it being multiplicatively close set already like that? Are we saying S is multiplicatively close set already?
Yeah. So we don't need this here. I'll put it back.
And that's the prime because multiplicatively close and saturated. Well, I guess smaller than 2. So doing
So,
one first.
2 implies, let's do 2 implies 1 because this is actually the easier way. It's going to be able to warm up for us. Suppose alpha okay, so our burden is to show that whenever I build such a set, well, actually, I'm gonna start with that. The first thing I want to do is I want to show that this is multiple. So our goal is to show that A times B is A. So A is in S. This implies that A is not in the alpha. Right, so AB is an S, so it's not here, so it's not in the alpha. And also B not in the alpha or from the alpha. So note if AB is in the alpha for any alpha, then A is in the alpha and B is in the alpha as the alpha, which is a constant. So AB can't be in any of those P alphas. Therefore, AB is in S. So AB is not in S complement, which is U the elements. Therefore, AB is in S. So it's multiple close.
Well, maybe on homework we can prove that if it S is a primary, it's basically a proper ideal, then
Let's now suppose that X, Y, R, and X, Y, and F. So now we want to show it's saturated. We need to show that these divisors are in. So X, Y is not in. Therefore, X, Y not in the alpha for all.
and I think the negation of like the definition of prime, then X and Y have to be.
The important thing here is that way. So therefore, neither X nor Y is in. And here, we're not using prime at all, we're just using ideal. Because if, for example, X is in P alpha, then XY is in P alpha, because it's vacuum, and same for Y. So, X respect to Y is in no. Therefore, X respect to Y is not in SC. Therefore, X and Y both are in S. So this establishes first direction. That is to say, if the complement is both saturated and multiplicative, or if the complement is a unit of prime ideals, then the set is saturated and multiplicative close. Let's do the other direction. This is the interesting one.
Then, of course, you know in the home part that that's multiplicatively close and saturated, then the complement is well, right.
That's for a single item. Let's do one in plus. Let's start by letting let X be an arbitrary element of the complement of S. The ideal generated by X, which I will remind you. Principal ideal generated by X is just every R multiple of X. It's disjoint from X. Because, and here what I mean by that is the ideal generated by X intercepts S. Yes, so. Right, because if there's something in the ideal generated by X, it's also an S. That means that there's an RX that's in S, but S contains its divisors, which can mean actually have to be in S. Right. So the saturation, anything that's here is the form RX. If it's also in S, because of the fact S contains its divisors, it would have to contain X. And that is a contradiction because X is in the complement. Yes.
Never mind. Yeah, you said it the first time around. I was like, oh, could you repeat that part? But you did.
Okay, gotcha. Now we can expand the ideal generated by X to a prime ideal, which I will know piece of X, such that piece of X contains X, and piece of X intersect S is empty. I guess. This is from the previous result. Right. What we can do is we know that X, so I'll draw a picture. We started here with X. We know that the ideal generated by X, this is S by the saturation item. And then we grow this up to piece of X, which is a prime ideal of this. And this is the big thing to do. Alright. Uh. Now, let me point out. The complement of S is just union. Everybody agree? By the way, clearly this is contained in this because every X is inside its P of X. But because all the P of X's live in the complement of S, you get the other containment, right? Because this covers everything in complement. And so we've got exactly unique. So there's Zorn's limit there. It was covered earlier, but there's some subtlety there. Anyway, that's a wonderful theorem that any saturated multiplicative closed set can be realized as the complement of the union of prime ideas. Okay, any questions? Okay, I gave y'all a little teaser last time, you know, and I did some stuff with fractions. I said, this is why we care about multiplicative closed sets, because when you want to add fractions in the traditional way we add fractions, you have a numerator and a denominator. And when you combine them, one way to do that is to get a new denominator that's the product of the old denominators that you're either adding to or multiplying, right? And this is why you need a set to be multiplicatively closed if you're going to make a new denominator, because old denominator, when you multiply that together, it's a new denominator. You need that to still be in your list of acceptable denominators, right? Now, this gives a process, an important process in algebra called localization that we're going to talk about now, and it's fractions. Now, most of this is easier than the first thing I'm going to do this in general, but in a lot of cases I'm going to specialize later. But I do need to show you more definition, more general definition. Let R be a commutative ring and S a multiplicative closed set. And S and R multiplicative closed set. Okay, let me say something about the assumptions that I'm under again. If you notice, I did not say with identity, because there's an important thing, you don't really need an identity for this, but our localization actually will create an identity for us when we do this construction. I also didn't say my multiplicative closed set doesn't contain zero. In most cases, you want it to not contain zero, but I'll show you this works even when it contains zero. But with zero, it's like a big fat flat tire, and I'll show you what I mean by that. We define an equivalence relation on the set Rx by we'll build up a little bit to this. You might think of R as your set of numerators and S as your set of denominators, although at first it might not look too familiar. I am going to consider R1, S1 is equivalent to the ordered pair R2, S2. If and only if there exists P and S such that P times R1S2 minus R2S1 is equal to 0. Okay. The set of equivalence classes of cross S modulo this equivalence relation, is written I'm gonna write it a couple of ways that you see. Sometimes it's written S inverse R. More commonly, we about R sub S. And it's called the localization of R S.
Is that R sub S? Or is that?
That is R sub S. That's R sub S. You know, you all have been working with equivalence relations since you're in grade school, right? You probably didn't really know it because we probably didn't talk about it a lot. But what is 1/2? That's right. It is -3 over -6. It's 11 over 22. It's 1 over 2. There's not a unique way to write 1/2. When you talk about that particular rational number, what you're talking about is a set of equivalence class. It's an equivalence class, right? All those different things are. And by the way, in the old days, if I give you a fraction, well, let me write this. Now, if I just walk up to you on the street and I give you two ordinary rational numbers, so these are all integers, how can you tell when two fractions are the same? What's the old trick they teach you in grade school, perhaps, or high school?
R1 over, or R1 times S2 equals S1 times R2.
Right, you guys remember this, right? The cross multiples have to be the same, which is equivalent to saying this. Right, that's what it means for two fractions of integers. Notice this is very close to this.
Yeah.
But you've got that extra widget there. Okay, so why is this extra thing here? It is to take care of the situation where you might have zero divisors, right? This takes care of this, right? Let me ask you a question. If your set S does have the 0 in it, right? Suppose that your multiplicative set S 0. How many equivalence classes are there? If 0 is an element of S, how many equivalence classes are there under this equivalence relation?
Oh, one.
Only one, because you could always take T to be 0, and this equation is always true. That means that if you have 0 in your multiplicative set, that there's only one equivalence relation, right? And actually, I'm going to show you that what we're going to do is we're going to build another ring out of this. And I don't know much, but I know a ring with only one element is the 0 ring, right? And that's why, so you can divide by 0, but it makes the universe collapse. Right? So you might try and see what the equivalence classes look like if you have, for example, R is Z6. Yes.
How does multiplying by some T and S take care of the zero divisor problem?
I'm going to show you.
Oh, I'm sorry.
It's going to actually come up in the proof, which I am also, not only am I going to show you, I am going to make you regret your question. Because we got to go through a little bit of computation, which is kind of a pain, but note I've sort of said this, but I think I need to write it down. If R has no 0 platform, and zero is not in S, then so this relation gets much easier if there's no non-zero zero divisors and zero is not an S, then this product being zero means one of these two has to be zero, and if it can't be T, it's got to be this. Also, the equivalence class of some ordered pair RS is often, and I will do this, written as R over S. So the equivalence does, think of this as numerator done. Right? That's what these things are. So these equivalence classes are just like fractions. Like I said, if zero is not in the multiplicative set, and you don't have any zero divisors other than zero, then what this says is two fractions are equal if and only if they're cross multiplied, which is what you used to. Yes.
You said if zeros in S, is it what equivalence class or what equivalence relation?
There's only one equivalence class, because what that means is this is equivalent if and only if there is something such as this product of zero. If you can let that be zero, that means every pair is equivalent.
Oh,
And so there's just one big fat equivalence class. Everything's equivalent to itself. Or everything is, all things are equivalent, I should say. Here is the big proposition here. Proposition 9.12. The set of equivalence classes forms a ring let me say at the beginning, using the notation of the previous, that is, R is a commutative ring, S is a multiplicative subset. It's supposed to be. These set of equivalence classes of RS forms a ring. Now, if I'm going to tell you it forms a ring, I've got to tell you how to add things up, and I've got to tell you how to multiply. So here are the operations. Number one, R1 over S1 plus R2 over S2 is R1 S2 plus R2 S1 over S1 S2. So this is the way I think you're used to adding fractions. And here, of course, R1 and R2 are the elements R, S1, and S2 are in S. So this actually forms a ring. And more than that, it's also got an identity. Even if the original ring doesn't, can anybody, maybe you might even rely on some intuition, what's the identity of this?
R1 equals this one. Like R equals this.
What's that?
R equals S.
That's the right try. if you take the fraction, if you pick any element of S and write S over S, that functions as identity. And it doesn't matter which S you pick, they're all equivalent. Right? So even if you start off with R being a ring without identity, this particular localization gets one. What is the first thing that I have to do? This is kind of big. So yes.
Are we assuming zero's not an S still?
Yes, but yeah, I'm gonna assume that. No. Well, we don't have to assume that here. If zero is an S, then this is all of which are crap because everything's equivalent, and this is basically the zero element of a one element ring. This is a zero element, and S over S is also zero, which is also the multiplicative identity and a ring of one element. Yeah, it's a bit of a mess, but okay. I think you can verify most of these details for yourself. It's probably going through this. It's painful, but I'm going to go through carefully what is first and most important thing to do here, and then I will at least give you an idea of how to move forward. Can anybody identify what is the first thing that we should do? I mean, I just made this wild claim. I put these crazy equivalence classes on here. Two fractions are the same if one with this weirdo condition. Right? And now I say, okay, you can add them using this rule. And of course, remember, these things are equivalence classes. There are many ways to write 1/2 and 1/3, for example. What's the first thing that I need to do coming out? Yay. Can anybody define the problem?
Probably just to make sure that that is an equivalence class, like the addition.
That'll be an equivalence class because this will still be an element of our localized S for the following reason. S is a multiplicatively closed set, so S1, S2 is an acceptable denominator. And this thing, certainly since R1, since Ri and Si are in the ring, this is an acceptable numerator. Right? But you're close.
Check it's actually.
So you're right. We didn't do that. We need to check that this equivalence collection. Maybe that. That's a good idea. Well, let's see here. The first thing we need to do is check, and transit's going to be the one that's going to be. Let's see if we can slide our way through this. Okay, first thing we need to do is check that everything's equivalent to a set. Right? Notice that I mean, this is already zero, so it doesn't matter what we multiply by, right? Therefore, well, okay, so far. Two, suppose these are equivalent. This implies there exists a T and S such that T times RS prime minus R prime S is equal to 0. I agree with that. Or therefore, right? Because the additive identity of that element is also zero. Slide that t in here. This is one of the rings how we can do. And this is equal to t times r prime s minus r s prime. Therefore, r prime s prime is equal to r s. What I do? And I'm going to preserve this here. So I think I'm actually want to write. That's a very good point. Now I need transitive. Transitive. Well, that's kind of yucky. So let's kind of go through this here. We need to show. We need to show that R over S is equivalent to R double prime the rest of it. Right? So let's write down what this all this business means. It means that there exists T and T prime and S such that T R S prime minus R prime S C prime and T prime of R prime S double prime minus R double prime S zero. Goodness gracious, what do we do with that? We multiply some stuff out, might make it easier to deal with.
Like substitute one in, like isolate a variable and then substitute.
Maybe. So I guess, see, I'm gonna need some kind of list. So let me see where we're going. We need to find that's our goal, right? So it's some scratch work, right? So really, I need to dispense. And let's see, I need an R paired up with an S double prime. And I need an R double prime paired up with an S. I don't see that anywhere. Any ideas on what we might do?
We'll probably multiply the top equation by S double prime and multiply the bottom equation by S.
Sounds like an idea, doesn't it?
Yeah, process of elimination.
Let's see what
that
happens.
first.
So we're gonna multiply this one by what? S double prime? P R prime S is equal to 0. Right? You guys better check this, make sure I don't get any of this. I'll turn around. And then I need, what did I need? I need also an R double prime hooked up to my S, so I'm gonna need an S here. S double prime S. minus T prime R double prime S prime S is 0. Everybody okay with that so far?
Probably multiply both sides by this top side by T prime and the bottom side by T double. And bottom by T and multiply top by T prime.
Okay.
To use the process of elimination to make it easier.
Okay, right, so what we're going to go for, I guess, is to kind of get rid of this R prime hooked up with this maybe. And right, so let's put a T prime in the top. Now multiply this by prime, it's by T. And so what do I get? T prime, R, S prime, S double prime, minus T, T prime, R prime, S double prime, 0. Multiply this bottom one by T, and T prime, R prime, S double prime, S, minus T prime, R double prime, S prime, S is 0. Everybody okay with that?
Then
Well,
just subtract.
now,
Add the two equations.
What's true about this, notice that I have, these two terms are the same. T prime, R prime, S double prime. So if I add these, I get T prime, S, or S prime, S double prime, minus T prime, R double prime, S prime, S 0. And I'm almost there. All I have to do now is
Just
pull out,
great terms.
S prime. I pull out the T prime, S prime, and I get R S double prime minus R double prime S. Notice T prime, and S prime are all in S, so the product is in S. This is multiple set. This is 0. So R over S is equivalent to R double prime over S. Exactly. Here, role C is being played by T prime S. Yes.
Are able to just multiply like the x's wherever we want? Like, is it continuative? Like, is S?
You've got these equations that are equal to 0. You can multiply them by anything in the ring that you want. Our strategy is I tried to build this up until these two things cancel out.
Yeah.
I think equivalence relation.
Like, because it's
You see that?
it's like first one, it's like TRS double prime S prime. It's like, are we allowed to just do?
I think it's because we're assuming R.
Oh, well,
Yeah,
the
we're-
order, yeah, I was sloppy in the order because the rings commute.
Okay.
Yeah, the rings commute. Okay, other questions? Okay, good call, Megan. Now we know that's an equivalence relation. What else do we need to show?
Figure operation tool.
The operations must be well defined, right? What I'm adding is equivalence classes. None of this is really hard. It's just tedious as all get out. This is the old chestnut where there are many ways to pick this fraction. There are many ways to pick this fraction. I could make two choices and get this answer. You make two perhaps different choices for the same equivalence class and get a different answer. Those two answers better be the same. And we're going to check that. I'm only going to check it with addition. It's the harder one. I encourage you to check it with multiplication as well. Suppose I'll look this way, R over S is A B. And R prime, S prime is A prime over B prime. Okay, so let's kind of go through this. This means let's T prime S such that T RB minus AS equals 0, and T prime R prime B prime minus A prime S prime is 0. You choose this fraction, I choose this one. You choose this fraction, I choose this one. And this is what it means for these fractions to be the same. Now, what I'm going to do in a similar vein to what we did before, let me take one more step here and write this out. TRB minus TAS equals 0. And T prime R prime B prime minus T prime A prime S prime is 0 as well. Now, what I want to do here is I am going to multiply this first equation by T prime, B prime, S prime, and the second one by TBS. And what I get, heaven help me, is for the first equation, I get TT prime RS prime BB. And I get TT prime AB prime SS. That's what I get when I multiply this first equation by T prime B prime S. And for the second one, I get TT prime R prime S BB prime and minus A prime B, this is prime. Oh, right. So I'm going to add these up. I guess I'm going to add these up. Yes, I am going to add these up. So, and I get a R S prime B prime plus R prime S B B prime. There's the first two minus T B prime A B prime S S prime minus T T prime A prime B S S prime. This, I have a TT prime that pulls out of. This is R S prime, BB prime, plus R S, R prime S, B B prime minus A B prime S S prime minus A prime T S S prime. And finally, what this gives me, PT prime times B B prime R S prime plus R prime S minus S S prime A B prime plus A prime B is equal to 0. Lord have mercy. So notice, this means this over this is equal to this over this. That is to say, RS prime plus R prime S over SS prime is equivalent to A B prime plus A prime B over B. And there you go. So you start with your fractions, I start with mine, and we get the same answer. Okay, any questions on this? As an exercise for next time, see if you can get through the following. Show that the multiplication is well defined, and this is actually a ring. The addition is associative, etc., etc. All the other stuff is easier than what we just did. Any questions? All right, I will see you folks on Wednesday. Oh.